The notes that we're going over here are to follow up with our last chapter, Unit 4, which were forces. So starting off with Newton's law of universal gravitation. So if you read along, right, when objects are close to the surface of the Earth, we can find the weight of an object by using the equation weight equals mass times acceleration. And that's what we were doing. We were taking the mass of something in kilograms, multiplying it by the acceleration of gravity, and that would give us the weight or the force of gravity acting on that object in newtons. Well, the weight of an object away from the Earth's surface, on another planet, on a moon, in deep space, it can be found, but you can't use the same equation, right? Because the acceleration of gravity is no longer 10 when you're on a different planet, or when you get away from the Earth's surface, it changes drastically. So we need to do something else. So we're going to use Newton's law of universal gravitation. So it says, every particle in the universe attracts every other particle. So you can also use this equation if you want to find that force of attraction between two particles. Let's say it was a pen and a pencil. You could find out the force of attraction between those particles using this equation. So it says that particles attract every other particle with a force that is directly proportional to the product of their masses. So directly proportional to the product of their masses. And you're going to see you need that later in the example problem. So as the mass increases, the force of gravity increases proportionally the same. Meaning if you double the mass of one object, then the force of attraction will double. If you take 1/3 the mass of an object, then the force that attracts them would only be 1/3. It's also inversely proportional to the square of the distance. So now, if you double the distance between two objects, the force of attraction is not just cut in half, right? That's inversely proportional. It would, as one goes up, the other one goes down. But it not only, as one increases, the other one decreases, but it's the square of it. So if you double the distance, then that means the force of attraction would only be 1/2 squared, or 1/4. And you'll see in an example later on. So it says G is the universal gravitational constant, 6.673 times 10 to the negative 11th. That's not a number that you will need to memorize. If it shows up on a test or a final exam, that will be given to you. So no need there. But you can see in the equation up here. So we have, right, in this equation, you have G, that constant, you have M1 and M2. Those are going to be the two objects that we're talking about, whether it's the mass of a pencil and the mass of a pen, if you want to find the force of attraction there, or whether it's your mass and the Earth's mass, and you want to find the force of attraction between you and the Earth, and that would give you your weight. The r squared at the bottom, that's that distance between the objects. So it says here in the second bullet, the force that mass 1 exerts on mass 2 is equal and opposite to the force mass 2 exerts on mass 1, which that wording should kind of sound familiar. It's Newton's third law. Right? If mass 1, let's say this is you, if you're being attracted to the Earth, then the Earth is also attracted to you. Those forces are equal to each other, but opposite in direction. Now, of course, if it's you and the Earth, you don't notice the whole Earth deal because the Earth has so much mass, it has so much inertia, it's really not going to move. So moving on, if the objects are large, Earth, Sun, etc., the distance r must be from the center of the object, not from its surface. So if you have a planet, all of the mass of the planet is kind of centered or considered to be centered in the center of that sphere. So you'll see in the example that we have where it's not just the distance between like you and the Earth, it has to be the distance between you and the center of the Earth. Or if you're on the moon, it would be the center of the moon. If objects are really small, then you can ignore, to the center of the object. And then the last one, it says, can be used to find the force of attraction between two objects, even if they're small, because of the attraction of mass to any other mass. So that's like I was saying, you could find the attraction of between you and your desk, or a pen and a pencil. You just have to put in the mass of the pencil, the mass of a pen, and the distance they are apart, and you would see that attraction. Okay, so we're going to do an example problem. We've got a satellite has a mass of 100 kilograms and it is located 2 × 10⁶ meters above the Earth's surface. So going back to what had done traditionally, right, before force diagrams, we'd list out the givens. So we have the mass of the satellite, ms, and the distance from the Earth's surface to the satellite, 2 × 10⁶, and notice it's in meters and kilograms. Those have to be the standard units that you add in for the equation. So the Earth has a mass of me, 5.98 × 10⁻⁴ kilograms. So that's our other object, right? We have the mass of the satellite, we have the mass of the Earth. And this gives us here the radius of the Earth is 6.38 × 10⁶. So we're going to have to take that into account because the Earth is so big. We have to go to the center of the Earth. So we have got 2 more givens there. So part A, what is the magnitude of the gravitational force on the satellite? This word magnitude, remember, it's just find the numerical value and don't worry about the direction, right? The direction is going to be towards Earth. So what is the magnitude of the gravitational force on the satellite? Well, it's pretty easy. You're going to use the equation, right? Notice that instead of m1 and m2, I put in what we're using here. So our 2 objects are the satellite and the Earth. And then notice down here on the bottom, right, we can't just have the distance to the satellite. Because you're dealing with the Earth, you also have to include the radius of the Earth in there. So plugging in those numbers, right, don't forget your gravitational constant. That's kind of a common thing that people will forget to put that number in. So 6.67 × 10⁻⁻11. We have the mass in kilograms of the satellite, the mass in kilograms of the Earth, and then the distance between them. And don't forget that you want to square that value. That's another common thing that people forget. Now, when you punch all of this in your calculator, being careful with the scientific notation. If I were you, I would hit second and then that comma button to get the E to show up instead of hitting times 10 caret and so on. But however you want to do it, hopefully you will get the same one. I would practice on your calculator and make sure you enter it right, because that's usually a common error. But the answer should come out to be 567.99 newtons. And that's it. It's pretty straightforward. You'll see in one of the homework problems you'll have kind of multiple objects. You're going to have like the Earth and a satellite and the moon, and you've got to figure out the net force. Well, the net force is going to be just like all those other examples. You know, find one force, find the other force, and then see if you got to add them together or subtract them, or if they're at right angles, you'd have to find the hypotenuse of a right triangle. Hopefully you guys will be able to kind of brainstorm and figure that out. So part B. If the mass of the satellite is doubled, you could redo the work above or use the relationship between the mass and the force of gravity. So instead of typing all this information in again, writing it all out again, and putting in 200, entering all of it in your calculator again, it's easier just to look at the relationship. Right? The equation shows it, and it was stated in the law, that force and mass are directly proportional. So if you have double the mass, all that means is now you have double the force. So if the force was 567.99, all you've got to do is double it. So 2 times 567.99 gives you the new force of attraction, 1,135.98. And that force will always be attraction, right? Gravity always attracts, it doesn't ever repel. Moving on to part C. Part C wants us to know if the total radius RE plus the distance above the Earth's surface is doubled. And that should say RS actually. If the total radius of the distance from the Earth's center to the satellite is doubled, what is the gravitational force on the satellite? Well, remember it's an inverse square. So what that means is if all of a sudden this distance here is doubled, right, but it's a squared value, So 1 over 2 squared is 1/4, and that tells you how the force is going to change. The force is going to be 1/4 of what it initially was. Well, it initially was this 567.99, so now, instead of 567.99, it's going to be 1/4 of that, or roughly 142 newtons. So that's it. You'll see at the bottom of the notes, you'll see there's 4 problems, and 2 of them will deal with this equation, where you're going to need to use this, and just be careful with that scientific notation. If you do need the radius of the Earth, or the mass of the Earth, it's given to you in this example, so you can refer back to it. So moving on. What you're going to see here in this problem is the angles of this object hanging are different. In every problem that we did, the angles were always identical. And so because they were identical, that meant that you know that the tensions in the y direction were always equal to each other. Well, in this case, because the angles are not the same, they're not equal to each other. What you're going to find out, and this is something to make note of so that you can kind of double check, is that T2, because it's more vertical, will always have a greater tension in it than T1. So when you find T2 and T1, compare them. If T2 isn't bigger, you know you've done something wrong and you've made some sort of error. So now also notice that down here we have this tension 3, and we kind of discussed that in class. You could just say it's the weight and kind of skip T3, but if it specifically asks for all the tensions, tension 1, 2, and 3, then you need to go through and you need to find it. So as far as the traffic light goes, right, T3 is pulling up, the weight, or Fg or mg, is pulling down, and so you can figure out that, right, T3 and Fg are equal to each other. So if we know the traffic light is 100 kilograms, that means it is 1,000 newtons, so T3 is 1,000 newtons. Okay, so notice this picture here, the 37 and the 53 have now, they look a little different than what they did in the diagram. Right? When you're looking at the diagram, this 37 degrees is measured from a horizontal surface, right? In this case, a ceiling or something. And so in this force diagram, you just match it up, and because this is from a horizontal line, right? Because it's from this line in here, then over here it's the same thing. It's from the y-axis. It's going to be measured from the horizontal. So you can match it up on the picture. Okay, so here's our tensions, right? We have T1, and that T1 could be separated into, right, T1, sorry, it's a little hard to write with my finger here, but T1y, and it would have a T1, oops, that's T1y, and this would be T1x, right? And our other object, right, it's going to also have a x component and a y component. And you really have no idea necessarily which one is going to have a bigger y than the other, and so it doesn't matter. Just try to make T1y and T2y look the same as T3 as far as magnitude goes. Okay, so to solve the problem, right, we're looking for now T1 and T2. We already know T3 is not 100 kilograms but 1,000 newtons. So to solve the problem, we must solve the two tensions into their x and y components, and then add up the forces in the x and y directions. So we know that the sum of the forces is 0, right? It's not moving. And so what happens is you usually start off with those semaphore statements for both the x and the y. Well, what happens is that when you look at the sum of the forces in the x, right, you'd get something like that, right? T1x and T2x. And then when you look in the y direction, you would have your T1y, T2y, and mg. Well, that's too many variables. We don't know the x components, we don't know the y components, because we don't know what these tensions are to start with. So we can't find the x and y components, and we're kind of stuck because we know that the y components are equal to the weight, but the y components are not equal to each other. So because T2y and T1y are not equal to each other, it makes it impossible to solve this equation. So we need to get, we've got 4 unknown variables, right? T1x, T1y, T2x, T2y. We need to get those down to basically 2 variables or 1 variable so we can solve it. So what we're going to do, and notice in this equation here I put the negative sign, right, because this one's acting to the left and this one's to the right and this one's acting down. I kind of showed direction before I put in the numbers, and you'll kind of see it looks a little different. But so what we need to do is we need to focus on our T1 x and our T1 y. So if you're looking at it, right, if this is this picture just kind of drawn in this right triangle, you can see that T1x is adjacent to the 37 degrees, which means if I use cosine, right, it will be T1x over T1. Right, so cosine of 37 equals T1x over T1. Now, it doesn't look that useful because, well, I don't know what T1 is, and I don't know what T1x is. So when I solve for T1 cosine 37 equals T1x, it doesn't do me a whole lot of good, right? Or it doesn't look like it. But what we're going to do is we're going to take this statement and we're going to substitute it in for T1x. Right? So instead of saying T2x minus T1x, we're going to say T2x minus T1 cosine 37. And we're going to do the same thing for T2x. Right? So if you're looking back, T2x, right, it's 53 degrees. So it's going to be the same idea here, except for it's going to be T2 cosine 53 degrees equals T2x. So we can substitute them in. So you can see now that the sum of the forces in the x have T2 cosine theta minus T1 cosine theta 1, and these angles here, right, theta 2 is going to be this, right, we're eventually going to put in here the 53 degrees, and for the other we're going to eventually put in the, what was it, 37 degrees. So you could look at it as T2 cosine 53 minus T1 cosine 37 equals 0. Okay, so instead of T2x and T1x, now we're just T1 and T2. Well, we're going to do the same thing here. Instead of T2y and T1y, we're going to get this down to just T2 and T1. So we can have 2 equations that just have T1 and T2 instead of 4 variables, right? Instead of 4 variables, we're going to narrow it down to 2 variables. So doing the same thing with the triangle, right? The y component is going to be the sine. So therefore, sine of 37 degrees equals T1y over T1. So T1y equals T1 sine 37. So again, we're going to go through and we are going to take this statement and substitute it in for T1y. And then we're going to do the same thing here. We're going to substitute in T right here, right? We're going to substitute in T2 sine 53 and then minus the mg. So what we end up with is T2 sine, again, this is going to be, let's see, sine theta 2 again is, right, 53 degrees. And this is, was it 37 degrees? So you can look at this now, and if you have this whole statement, right, T2 cosine 53 minus T1 cosine 37, and you have this whole statement, we've just narrowed it down now to 2 variables instead of 4. We didn't know T2x, T1x, T2y, T1y. Now we don't know T1 and T2, or T1 and T2, right? But it's only 2 variables. Well, if you have 2 equations and 2 unknowns, what do you do with it? You set them equal to each other. So we now have 2 equations with 2 unknowns, so we have to set up a system of equations and use substitution. So if we have this T2 cosine theta 2 and T1 cosine theta 1, right? Because this is negative, right? The 2 together add up to 0. So if I move it to the other side, I get this, right? Now I'm going to either choose to say what T1 equals or what T2 equals. It really doesn't make a difference. Just pick one. So in this case, I chose T1. Right, so isolating the variable of T1, you get T1 equals T2 cosine theta 2 over that cosine theta 1. Now, plugging in the numbers, right, remember theta 2 is 53 and theta 1 is 37. So you can now substitute this in to here if you wanted to, right? Or you can take this further, and that's what I do because that's just too much stuff to write down. Basically, it just looks kind of crazy when you got all these cosines at different angles. So I just did cosine 53 minus cosine 37 in my calculator, right? And that came out to be 0.7536 something. I took it to 4 decimals. I know I'm going to round my answer to 2 decimals, so that should be plenty to give me an accurate number. So now I know that T1 equals 0.7536 T2. So doing that substitution, I'm going to take this, and in my sum of the forces in the y, right, I'm going to, instead of putting in T1, I'm going to put in 0.7536 T2. So if you do that, oh, I moved mg over to isolate it. So now I substituted in, right, theta 2 was our 53 degrees. Instead of T1, I now have 0.7536 T2, right, in here. Don't forget to keep the sine 37 degrees. And then I have mg over the side, right? We said that it's basically weight. Tangent 3 was equal to the weight, which was 1,000. Now, if you look at the equation, finally, we're down to 1 variable. Only T2. So now you just do your algebra. Right? Sine 53 is 0.7986. Sine 37 times 0.7536 is 0.4535. And then we have 100 times 10 is 1,000. You don't have to show this step. You can just go from here right to the answer. But just trying to move it along, right? You're going to add these two together to get this 1.2521. Now I'm going to figure out what T2 is, right? So 1,000 divided by 1.2521 gives me the answer of 798.64. I now know that T2 is 798.64. Well, remember, we've got this equation up here, right? Well, if T2, right, we now know that T2 is that, all you got to do is put it in, right? If T1 equals 0.7536 T2 and T2 is 798.64, plug it in. 0.7536 times the 798, and we get our answer, right? T1 is less than T2. Remember, this is the one that's more vertical, so that's good. We probably did it correctly there, and you got your answer. So when you're looking at these 4 homework problems, you'll see homework problem 1 and 2 are basically like that example we just went through. They're identical. You can follow the same process with these different values for the weight, right? Make sure you turn that, and then you have different angles instead of the angles that were up there. But the process is exactly identical. You just got to go through it. And then number 3 and 4 are using the equation that we started off the notes with the universal law of gravitation. So good luck, work in small groups and get those done, and that's it.